This is the 10th in a series of screencasts on the subject of reaction dynamics for the module CHE30042. So today we're going to basically finish up talking about reaction dynamics by talking about amendments to the Lindemann theory that we've covered in the previous two screencasts 8 and 9. As usual, there's some associated reading with this. Again, I've linked to this textbook which has some useful information in these chapters here and pages here, and once again, just to remind you, this QR code takes you to a page from which this book is available, and you can get access to that page for 2 weeks for free. Okay, so once again, if you want to revise this topic using this book, you can do that, but probably do that right at the end of all this. There's a link here to the book Reaction Dynamics by Bruard. And on page 68 and 69 in particular, he talks about some of the theories that we're going to talk about during this screencast. And again, this QR code takes you directly to those pages. I would say that this book is a tougher read, as it were. It's a bit more theoretical and probably aimed at postgraduate level, not at your level, but nevertheless you can get some useful information out of that, particularly if you are more mathematically inclined. And then finally, and possibly the most usefully, we have this book here, which is Chemical Kinetics by Laidler. And I essentially have a QR code here to a PDF that's available online for the specific chapter that we want, and within that, pages 155 to 163 are particularly useful. Okay, after 163, the text goes into some other theories, of which I will allude to right at the end of this screencast, and if you do download this PDF, you can have a look at those there. Okay, so why do we need amendments to the theories we've talked about already? Well, we've said this at the end of the previous two screencasts, essentially. We've found issues with the theories, okay? The theory is very good at describing the pressure dependence in a sort of qualitative way, in the sense that you see a first order pressure dependence at very high temperatures. You see a first order reaction, whereas at lower temperatures you see a second order reaction, and we explain that by sort of making approximations at the bottom half of this equation here. But when we tried to use this theory in a more advanced way and tried to start saying, well, if this is the case, we can linearize this equation somewhat and generate a Lindemann plot, essentially by rearranging this to pull the concentration of A out to here, and then you get left with the rest of it, which is your observed rate constant. And if you plot 1 over the reserved rate constant versus 1 over the concentration of your reacting species A, you'd expect it to be linear based on the Lindemann plot, but it is not, and you can kind of see this kind of deviation, particularly at higher pressures, higher concentrations. And obviously on this graph, higher pressures, higher concentrations are at lower 1 over concentrations pressures. So this is what we typically see. We see it matching the theory-ish at low pressures, but not at high pressures. And the other issue which we highlighted in the last screencast was that collision theory. If we try to use collision theory to predict one of the rate constants, in this case K2, then it's horrendously underestimated. Now, and basically the reason for this, and so sorry, this underestimation is shown here in this table here. So I just screen grabbed the table that we showed, but if you don't recognize this, go back to the previous screencast and have a look there. The main issue with the theory so far is essentially that internal energy isn't considered, and we already mentioned this right at the beginning when we talked about collision theory in the first few screencasts. We said that collision theory doesn't take into account internal energy, and that's particularly important for these kind of reactions, because these kind of reactions are we are explicitly making excited states, and so therefore we really do need to consider internal energy. So we've got a couple of amendments that I want to talk about in a little bit more depth, and we'll see how well these do. But both of them, essentially, the underpinning thing they're trying to do is to consider the internal energy of the reactions in the different steps. Okay, so the first thing we're going to talk about is the Hinshelwood amendment, and this basically improves the prediction of this K2. So K2 being that rate constant that looks at the activation of the species. So you've got your species plus another thing banged together to make an activated species. Okay, and that's got the rate constant K2. What the key point about the Hinshelwood amendment is, it says that the energy that is gained, or the reaction activation energy that's gained, is going to be distributed amongst all of the vibrational modes within a given molecule. Okay, so essentially it's saying you've got an energy within the molecule, and if that energy is greater than the energy required to form an active species, then it's possible to form that active species, regardless of whether the energy is in the right place or not. Essentially, the energy can sort of, vibrate into the right place, and statistically, there's a probability that that would happen, and it takes that into account, basically. So, what Hinshelwood did is he then wrote an equation, or derived an equation for the fraction of molecules having an energy greater than this particular energy, and this is based on the same equations that we used at the beginning, based on the Boltzmann distribution. We have very similar things at the start, looking at for collision theory. Okay, so this F would still be the fraction of molecules having an amount of energy. Okay, obviously we're introducing some new terms here. So S in this case is the number of vibrational degrees of freedom. Okay, and this E0 with a star, this is the energy required to make an active species. And of course, this energy, in order for a reaction to occur, needs to be in the right place. But Hinshelwood's saying that as long as you've got enough energy within the molecule as a whole, eventually it will go into the right place. And of course, the bigger the value of S, basically the bigger this additional term, which is additional to the normal kind of fraction term, which would just be the exponential bit here, gets. Okay, and we can see that on the next slide. Okay, so if we put this lot in here into the Hinshelwood amendment, into the rate equation. Okay, so if you remember back from collision theory, the rate constant is equal to essentially the sort of collision density, the number of collisions in a given amount of time, multiplied by the fraction of collisions that have enough energy. So essentially, all we've done here to make a rate constant is adding in this molar collision frequency. And then we've got this bit here which says, how many of those molecules that are colliding have the right amount of energy. Okay, so that's basically the same as what we've seen before. Key point here is that this E star 0 is not the same as the activation energy for the reaction. It's actually a little bit bigger. Okay, and this is the relationship here. And if you want to see that being derived, then have a look at the e-book that I was talking about at the beginning, that sort of chemical kinetics book, on page 156, 157 particularly shows this being derived. Okay, so what's the result? Well, if this is the Lindemann theory that we've talked about so far, this is essentially just collision theory. You've got your Z and your F, which is just the exponential term. Okay, and of course Hinshelwood brings in this additional term here, okay, which is dependent on the number of vibrational modes S. And the impact on this, I've just essentially put a table together here. These are different values of S, and this is the amount that this is equal to for a given ratio of energy over RT. So this is energy over RT is equal to 10, 20, 40. And you can see, even at just 8 vibrational modes, which isn't a particularly big molecule, you can see here that this term increases the value of K2 by many orders of magnitude. So that's kind of 32 million times bigger. Yeah, 30 million times bigger. Okay, so it's a very, very big difference. Of course, this part here is going to get a bit smaller, which is why I've said the excluding exponential term, because obviously this value is bigger. But this gives you an idea. It's not going to get smaller by the same amount, is it? Okay. So that's great, but what's the problem? Well, there are a few problems. First problem is that this theory doesn't make any difference to the Lindemann plot. Okay, so the Lindemann plot would still be expected to be linear using this theory, and that's why actually when you see in books Lindemann plots and you see the theory line, often the theory is referred to as Lindemann-Hinshelwood theory. Okay, and that's basically because even when you include the Hinshelwood amendment, that the plot is still linear. The second issue is that actually the value of S you require in this equation here, the Hinshelwood amendment equation, to get a good fit, as it were, so to get the same result as the experiment, is actually about half of what you'd expect it to be for a given molecule. Okay, so if you know in your molecule, you've got 10 modes of vibration, typically this value of S would end up being 5, for example. So that means we can't really predict it, doesn't it? You might just say half of it is probably likely, but still, it's not satisfactory. And the final problem is that if you look at this here, I mean, obviously this Z term here is proportional to T to the half, and that's collision theory. But you now have a new temperature dependence coming in to the pre-exponential factor. And this actually is not observed via experiment. So this is something that, again, isn't satisfactory because we don't have any experimental evidence for such a temperature dependence. That suggests that this term isn't quite right, even though it's doing the right thing. Okay. So moving on, the next amendment is the RRK amendment, and this amendment affects the whole thing. Okay, so it looks at all the different rate constants and it will make a change to every single one of them. Now basically it says that all of the rate constants are going to now be dependent on the energy that's actually in a molecule at the time. And that's why it changes them all. But the result for K2 and K-2 is pretty much the same-ish as the Hinshelwood one. The major change is in the conversion step. So that's the one where you've got essentially your activated state going to products, which has a rate constant of K1. And this step is actually typically overestimated by collision theory. And the reason for that is basically because, again, the energy needs to be in the right mode for conversion to occur. If it's not in the right mode, obviously, the reaction's not going to occur. So you need some sort of statistical explanation for the energy moving from just being in the molecule to going into the right mode. And the way that Rice, Rampertsberger and Castle, which is the RRK in this, introduce this is by basically saying, yeah, you can make your sort of activated state A star, but then there requires to be some shifting around until you can get to the transition state, which then will convert to products just via essentially this rate constant K, the transition state double dagger symbol. And we met that already in transition state theory, didn't we? This is essentially the same as the vibrational frequency of the bond that's changing, essentially that kind of bond that's breaking, maybe. Okay, so we get a new expression using this kind of treatment and this statistical expression, and there is a bit more information about where this come from on these pages here, but I didn't really want to go into it in too much depth now because it gets quite nasty and mathematical, and it just doesn't seem like the best use of our time. The U expression essentially says this, okay, that you have got something that is related to the energy now, and key point here is that essentially K1 will increase as you have more energy around, okay, more energy in your model, and that's just basically because you've got a higher probability of the energy being in the right place because you've got more of it, okay? But the other key point is that K1 will decrease as you have a bigger S, okay? And so for bigger molecules, K1 is going to be effectively smaller, and that's basically, again, because you have more modes, so the energy might be split over more modes, and there's less possibility for it to all filter into the one correct mode. Okay, so sort of just to sum this all up and put it all together, we just need to go back and we need to say, well, both of the issues that we had before were that, energy dependence of these things and the energy being in the right place wasn't really being taken into account. That idea of having internal energy perhaps already, or it just being there but just not being in the right place, wasn't taken into account in both steps. And obviously in the case of K2, this led to an underestimation of the constant by collision theory, and in the case of K1 it led to an overestimation, and both of these have been sorted out by the Hinshelwood amendment in terms of K2 and also by RRK theory in both cases. Okay. The issue is that in both cases we have this problem with the value of S. It's not what it should be in both RRK and Hinshelwood amendments. Okay, and that remains as an issue. Okay, So there are more advanced theories that have come along. One of which is Slater's treatment, in which essentially he said that multiple modes of vibration might contribute to the reaction going ahead, but he didn't actually allow for flow between these modes, and that's really where the theory broke down on many molecules, and that's because that's basically not very visible, particularly in certain parameters. So this is a failed theory, but one that was quite useful at the time. And again, if you want to read more about this, there's some information on this in the ebook that I linked to right at the beginning. And the second one, which is rather better, is essentially this RRKM theory. So this is an extension of RRK theory by Marcus, and that brings it a little bit closer to transition state theory. Okay, and one really nice thing about this, which sort of brings all of collision theory, all of the reaction dynamics that we've been talking about so far together, is that at high limiting pressure, so this kind of K infinite that we've been talking about for the last few screencasts, will tend to the same expression as we got for the unimolecular reactions according to transition state theory. And that explains, if you go back a few screencasts and you remember, we said, in certain cases, transition state theory can get pretty close to predicting the correct answer for unimolecular reactions. Well, RRKM theory is giving the same response, and this is kind of joining those two things together. Okay. So essentially, that's the end of reaction dynamics. So thank you very much for listening, and that's everything.